get embarrassed just showing up, much less than talking nice about me. I'm not used to that, you know. Usually I walk into the room, and by the time I get in there, there are, you know, people are making jokes about me and all kinds of stuff. Of course, I kind of deserve it, because I kind of dished out a little bit. Well, first of all, let me apologize for being here today, because it sounds like if I wouldn't have been here, you would have had 2 days off. So that's my apologies to you. It's worth your while showing up today, but we're going to have a good time. First of all, let me start out by asking, how many of you guys are seniors here? Guys and gals? Woo! Is everybody a senior? You've all signed up for graduation? Is that right? Okay. I heard them talking outside. Today's the deadline or something like that. So, if you want to be a senior next year, you might want to think about that. A little bit about me. I got a bachelor's degree from the University of New Mexico, a master's from BYU, and a PhD from University of Utah. Notice I'm going to highlight it. I always have to make sure I get the right presentation. You know, it's even worse if I do this one up there. Oh, that's not good. So yeah, so I've got a PhD. I did work for the department. I was responsible for a lot of the automation in the lab over there. Before they used to have a baby network 90 system over there. We got that donated. Look at her shiver and shake. Look. Now I guess they replaced it with something. Anyway, anyway, that was kind of my contribution. I taught some control classes while I was here. When I went to Set Point, I actually went all over the world and just about anyway, a lot of Europe, a lot of time in Japan, you know, Norway, Spain, Germany, Italy, France, doing advanced control. And what we did was fun stuff. It was good stuff. I remember when I was graduating in process control, and chemical engineering with kind of an emphasis on process control. There really weren't a lot of companies that came to BYU looking for people in process control, and there probably still aren't. Okay, BYU is not known as a great process control school. We think that's going to change. Dr. Hedgren is fantastic. I'm thrilled to death that he's now a faculty member down here. There was a fellow that worked with me, his name is Scott White. Scott's one of the smartest people I ever know. He's now my vice president of my company. And he's as close to a genius as I've ever met. And I remember when Scott and I left, we had a passion for process control, but not a lot of other people did. And so when we left, kind of the drive for the program died out, and we've been begging partner for 15 years to try to get somebody in control. And Dr. Hedgren is the result, not a result of us, but the result of the department doing that. And we are just greatly excited, appreciative for that. Let me just tell you a little bit about process control. You guys said you're all seniors. Why do you think you're taking the process control class when you're seniors? It's more applicable. Let's go ahead and go through some of these slides real quick. Work that a little. No. Come on. There we go. Well, the reason we do process control is it's almost always economics. You know, when you go out and talk about, you guys have learned a lot about different kind of process operations, haven't you? You've had heat transfer, mass transfer, in that right now. Okay, separations, okay, thermodynamics, fluid dynamics, kinetics, reactor design, okay. What happens when you go out in the real world and start using all that stuff? Where does it go? Put it in a plant somewhere? Don't you think? I mean, it's great to have it in the computer. I know you guys are all computer gurus, but when you get out in the real world, you think you mess around in the computer all the time? Is money made in the computer part of it? The money's always made when the plant is built, right? So the operation is not a computer. The operation are a bunch of pieces of equipment and stuff like that. So all of the work you've been doing up to this point has really been so that I can design something, so I can build something. I can make it work, right? When you do that, you want it to have good quality, you want it to have great throughput, yield, be environmentally conscious, energy conservative. Want to have great uptime. You guys know what uptime is?
How much time it's actually running?
Yeah, the fraction of the time it's up. You know, so you want to keep it up all the time, right? As much as possible. And safety. You want to do it safely. Okay. Come on. Building a plant or doing process control or anything else is almost always the same. Okay? Who here has had any experience in construction? Any? Who's seen a house built? What's the first thing they do when they build a house? They dig. What do they put in that hole? Basement. They put up walls. They put in a good foundation. They put on a good floor. And then they start working their way up, right? So this is kind of like, oh, that's a great page. My backup page. So this is very much like what we do in chemical engineering. You guys have gone through all these classes and teach you how to build reactors and distillation columns and tanks and towers and pumps and pipes and all the other stuff. By the way, when I would drive by a refinery, you guys driven by refineries? Aren't they sexy? Us chemical engineers, when we go by refineries, we get excited. All right? I'm just telling you. I don't know about you guys. I drive by and I see all those pipes. Oh, man. What kind of pipes are those? I have to tell you, it's great. Okay, so we put together all those pipes and towers and tanks and all this other stuff in the plant. And then what do we do on top of that? What do you put on a foundation? A frame. In this case, you're going to put on some instrumentation because as good an engineer as you are, you think if you just put in pipes, oops, I'm doing that. If you put in pipes and all this other stuff, it's just going to run? Is that what happens? You just put it in and bat your eyes or blink or snap your fingers and all of a sudden there's stuff running through it? Is that the way it works? No, you have to have instrumentation. If you're going to drive a car, do you want a speedometer? Do you want brakes? Do you want a windshield? Want to see what's going on? Yeah, it's all great that there's a car, but you probably want wheels on it, you know, tires, a windshield, stuff like that. We've got to be able to see what's going on. Above that, we do what we call regulatory control. The regulatory control controls the basic. Does your car have any regulatory control on it? What is the regulatory control? Any ideas? Go ahead. Temperature? Temperature? Yeah. So does your car overheat? Yeah, most of the time. I have a daughter that her car just overheated last week, so I had to go save her. You know, anyway, so that was fun. I used to be a mechanic, so that's how I paid for my undergraduate education. Anyway, so yeah, we don't want our car to overheat. That's bad. You know, for me, things are either good or they're bad. Bad, good. The car, regular heat, controlling the heat in the car, good. Okay. All right, we have to have instrumentation. We have to be able to sense the temperature. We have to be able to know what's going on. We all want to know how fast we're going. We all want to make sure our battery's not going dead. We all want to do all these different things in the car. We do the same thing in refineries. Make sure that the level of the tank's not too high or too low. We don't want it overflowing. We don't want to run it empty, right? Pretty straight and simple stuff. Okay. What Dr. Hedgren wanted me to concentrate on today is how you use your engineering skills to be a good process control engineer. Let me just tell you right now that the key to good process control is getting the control and the process to work together. The key word in process control is process. If you understand how the process works, actually the control becomes very easy. Okay? You guys may think that's kind of odd right now as you're starting to study Laplace transforms. Why do you study Laplace transforms? Anyone know? Who's it telling? No? Builds character? You know, I have a Dodge Durango, and I drive up on the curb sometime. My wife says, "Why'd you do that?" Because I can. That's why, you know. Go ahead, I saw a hand going back there. Why do we do Laplace transform? Laplace transforms turns ordinary differential equations. Who likes solving ODEs? No. Ooh. Okay. Turns ODEs into algebraic equations. Which would you rather solve, an ODE or an algebraic equation? Yeah. That's what I'm talking about. Okay? So just know why you're doing it. Okay? In the real world, when you go out and do process control like I have for the last 25 years, I haven't done a Laplace transform in, I've probably done 5 in the last 25 years. Okay? So, but for the stuff that you're doing right now about learning about modeling of processes and stuff, and characterizing processes, you kind of need to know Laplace transform. Okay? So it's a useful tool. Knowing the process characteristics is the first step in implementing good control. Processes with different characteristics require different control techniques and tuning. There is no one-size-fits-all tuning technique. Okay? So what's the key to getting good process control?
Understand the
Understand the
process.
process. So here at APCO, I've got a company, I've got positions open. Okay? I have a hard time filling those positions. Why? First of all, I prefer to hire chemical engineers. Why do I prefer to hire chemical engineers? They have exposure to more processes than any other engineering field. Okay? My second on the list would be mechanical engineering. So if I want to control a distillation column, who would I need to go to? A chemical engineer, right? Or a reacting system. Who's going to be best at that? Probably a chemical engineer. If it's a fluid flow or a pump or a heat exchanger or a mechanical system or manufacturing system, would a mechanical engineer be good? Absolutely. Absolutely, okay? But can a chemical engineer do those kind of systems? Yes. Okay? So there's more breadth. You guys should be proud of that. That's one of the things we have. The goals of process control are to stabilize the process, reject measured and unmeasured disturbances. Whatever you do in your design in heat transfer or chemical kinetics or whatever, except for maybe, I think they have a few minor problems, but almost everything you do is what we call steady state, right? You design a CSDR, steady state. PFR, what's a PFR? Hey, you guys are my heroes. All right, y'all passed the entrance exam to APCO 8. That's not real hard. Okay? So, anyway, a plug flow reactor, any kind of thing like that, it's always designed around steady state. How many processes do you think actually run at steady state? Zero. None. Okay, so they design them around steady state. This happens all the time. They pay me big bucks to go out with refineries, chemical companies, things like that, to do P&ID reviews. You guys know what a P&ID is? Process and instrumentation diagram. And they say, tell us what's wrong with the controls. And the guys that design the controls are the guys that do all the steady state stuff. And they say, you know what? I can control the vapor pressure on this front distillation column because it's connected all the way down through the process to this intake. So I'll control the vapor, the pressure down there, and that controls the whole thing. And I go, okay, and I shake my head. I say, shame, 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 shame. No, I don't really say that, but I think it, you know. And then they start criticizing me. Now you see how the whole thing goes. So you have to understand about dynamics. It's difficult for me to say, hey, I'm going to control something where if I see a variable now, I'm going to make a change a half an hour from now when I see it at the end of the pipe, and it's going to be able to get good control at the front. Does that make any sense? How many of you have ever had a car that had a carburetor on it? It's gone from like 98% of the class with one guy. That's how old I'm getting. I'm telling you, it's bad. It's really bad. Okay, the carburetor gets a little. You hit the gas hard right at the front end, and what happens? Nothing. Nothing. If you hit the gas hard on the front end of a refinery, nothing happens. What are you going to do? You're going to hit it harder, right? You're driving your car, you push the gas, nothing happens. What do? Push it harder. So then when it finally catches, how fast are you going?
Too fast.
A little too fast. Okay? Okay? So understanding that and just understanding the relationship between when I make a manipulated variable change, when I make a change in the process, and how it affects the process, not only at steady state, but between now and steady state is an important concept, right? Okay? That's what you guys are learning about. Okay? It's a very important thing. Okay? We account for process interactions in a control scheme. How many of you guys ever been in a home with 2 showers? Or with a shower and a toilet? You're in the shower, the toilet flushes, what happens to the water temperature? Huh? Ice cold? Who said ice cold? Who said ice cold? Not unless your toilet's hooked up to the hot water. I wouldn't want that. All right, that's not good. So being able to reject that interaction would be nice, wouldn't it? Okay, that's what we do. So we say, hey, look, we know if this is going to change, this is going to change. And we can take that into account. How do we know what's going to change? Intuition. Intuition. Oh, intuition. That's a good guess. You sure you're a senior? Go ahead.
That's experience in the plants.
That's experience. Oh, we're better than that. We know what's going on with the process, right? So if I flush the toilet, why does the water get hot in the shower? The water pressure drops on the cold side, right? So there's more hot water than cold water because the pressure is the driving force for flow. So the water gets hot while the pressure's down. See, we're pretty smart guys. We can figure out how a toilet and shower work. And we're pretty good, okay? That's all it is. If you go out to the plant, it's the same type of thing. Okay, if they open a valve on one side, what happens to the pressure on the other side? It drops. So what happens to the flow on that side? It drops because pressure is what drives flow, right? Okay? You see, so it's not real complicated, but since we know it, does the computer know those things? No, computers are really dumb. They really are. Computers only know what we program into them. All right? So process control is at least 50%. At least 50% saying, look, I'm a good engineer, process engineer, and I'm going to take what I know about the process and I'm going to build that into the controls. So does that make any sense to you? So I know if the pressure drops and the flow drops, maybe I should drop the hot water flow too. So maybe I should control the ratio of hot and cold water to the shower head. That makes sense to you? So if I control the ratio of hot and cold water to the shower head, when the toilet flushed, would I get a hot water surge? Well, the pressure would drop a little bit, but the water temperature would stay the same, wouldn't it? Okay? One of the reasons why we like to reduce variability is because we like to come up almost always the optimal place. The TA is the optimizer, Mr. Optimizer there. Okay? The optimal place to run a plant is almost always at a constraint. Okay? Why do I say that? Anyone have any ideas about that? Why is the optimal place almost always to run at a constraint? If I design a tower or a plant to run at 10,000 barrels a day, okay, they usually want to run more than 10,000 barrels a day in that plant. Why? They make more money. See, the capital cost, the cost of the tank, the cost of the pumps, that's a fixed cost, right? Okay? But I know for every barrel I put in, I'm going to make money on it coming out, right? So how many barrels do I want to push through there? As many as you can, right? See how that works? It's really quite simple. It's nothing real complicated. You say, hey, I want to push as many as I can. Pushing as many as you can means you're going to push that refining harder and harder and harder until you do what? Break it. Until you come right up to the edge, you break it, right? You don't want to break it, because if you break it, it stops, right? If you break the car, it stops. Yeah, I had a friend, I like motorcycles, but we go out single track in the mountains. I had a friend who bought a KTM 300. And he was so proud of that KTM, it was really fast. So he actually an employee of mine, he used to go riding all the time. So he took that KTM, he took it up to 95 miles an hour. He said, man, he had that baby maxed out. It was doing great until what happened? They blew the engine. Whoops! That was all great, but yeah, no. But we don't want to blow the engine, right? You walk on how many of you have ever been out to some cliffs, you know, Yellowstone, or not Yellowstone, Grand Canyon, or wherever, you know? The blocks go up. Who wants to see how far down it is? Come on, admit it. Aren't we a little bit kind of, you want to see how far down it is? So what do you want to do? You go right, wait, who said crawl? Throw a rock, listen for how long it takes. How many of you crawl over the edge and look over? Or stand over the edge and look over? You'd stand up there? You did? I laid down. You're hired. Surprised you're here today. We went down, we were down on a motorcycle thing, we were riding down in the Book Cliffs or whatever, I don't know, we were down there were some pretty good cliffs down there, so we're riding around and we stopped, take a little break, and there's this cliff right at the edge, and there's this guy that works for me, he's standing over the edge, hanging his leg off the edge, woo! And I'm just shaking. I'm way back, I'm like, oh, I just can't watch, What is my problem? Can you guys tell me what I'm worried about? A wind's gonna, blow, there's gonna be some kind of disturbance. Right? Who knows? He's gonna have a kink in his muscle, a twitch, I don't know, he's gonna sneeze. It doesn't take much, right? Can't run by the head and over the cliff. What happens once he falls off that cliff? There's no turning back. At that point, I say, told ya! As he hits the bottom, probably. That's not the best thing in the world to do. So that's the way processes are. Processes, for example, a distillation column, the limitation on a distillation column, you guys have had separations? Are you in it right now? Okay, so have you studied distillation columns at all? Do you know what's called, you know what flooding is? What is flooding? Liquid, not water. It's usually liquid. It's not usually water. Liquid. It fills between the space, the vapor space, and goes all the way up to the next level. Okay? And once you do that, once you flood a column, how much separation do you get? Zero or close to zero, right? Once you hit that constraint on the distillation column, you're done. You know what you do? Turn off the heat on the bottom, you turn off the reflux on the top, you let it drain. Start all over again. Okay? So, flooding is the capacity constraint of a distillation column. Does that make sense? If I try to put too much liquid through it and too much to do the separation, pretty soon it can't handle it, so it backs itself up and it's called flooding. Alright? You either get jet flooding or liquid flooding, it doesn't really matter, it's going to flood. When it floods, you're in the thing. So what do we want to do if I'm trying to make as much as possible? I want to get as close to that flooding constraint as possible without violating. So there's the difference. If my process is bouncing around like crazy, and I reduce it by the deviation by half, what's my new average flow? See, I'm closer, aren't I? Is there any money in that? How much? Like pennies, nickels, dimes? We'll go back to this slide in a minute, but let me come back to that slide in a minute. Let's look at this here. So that's a distillation column where I reduce the standard deviation. This is in, I forgot to put the number, 1995. Okay, this is the value of isobutane. You guys know what isobutane is? Oh, you guys studied your chemistry well. Versus normal butane, right? Isobutane is worth a lot more than normal butane. Okay? Because isobutane has got very high octane. And it can also be used in other chemical reactions to make things called alkylate and other things that are high octane. Okay? So the value in 1995 $65 a gallon versus 30 cents a gallon for normal butane. I said, look, if I can reduce your standard deviation by 50%, and reduce the loss of isobutane by 2.3%, that ends up to be $312,000 a year. That's a 1/2 of one distillation column. So this is for the Flying J, or now Big West Refinery up in North Salt Lake. Okay, and I'll tell you, when I went in and I did the analysis, I thought, I think I could make you $500,000 a year on the whole gas plant. Okay, so they said, okay, go ahead and do the project. We don't believe you. It's just computer programming. How much can you really do, right? Changing the control software. So I estimated I could make them $500,000 a year. You know what? How much I made them? $1.2 million a year. Okay, costing about $100,000. So if I gave you $1 and said, if you give me $1, I'll give you $10 at the end of the year, would you do it? Pretty good return on investment, isn't it? Okay. That's the kind of stuff that process control does. But I'm trying to focus on how your engineering skills can help you work. How many of you in here know about the Antoine equation? You just heard of the Antoine equation. Every hand in the place should go up, right? You learned about that in material and energy balances. What does the Antoine equation do? Vapor pressure. So the Antoine equation can give us information about varying pressures in a distillation column. So if I increase the pressure or decrease the pressure in a distillation column, the separation changes. Do you know that? So the problem is that they want to control the temperature to control the separation, but the pressure is jumping all over the place. That's a disturbance, right? See how that works? So the pressure is a disturbance to the separation, isn't it? Okay? So we did what we call pressure compensated temperature. So you see this black line in the bottom is the analyzer. Okay? That's isobutane. The bottom line is the amount of isobutane going out the bottom. That's how much they want to go out. Okay? And that's based on a steady state analysis, by the way. This is the actual data. Each one of these little bumps you see is like 40 minutes or something like that. So this is probably a few weeks data or even more. This is the temperature in the column. So there's two different things here. One of them is, the blue is the actual temperature, the green is the pressure compensated temperature. So what happened in this column up there, they have air cooling. We're not by the ocean. In the ocean they always use, or near the ocean or water, they always use liquid heat exchangers for the most part, okay, to do their cooling. They got a lot of cooling water there, right? But up here in this dry, arid desert, we have a lot of air. So we use what they call big bang heat exchangers. You've probably seen those in the lab. Those are very simple compared to what they use in industry. But they use these box exchangers. What happens on the hottest days in the summer? It's hot. And they get enough cooling? No. So what happens if they don't get enough cooling? Pressure goes up, right? EV equal nRT, temperature goes up, pressure goes up, okay? So here's this green line here. That's the blue line is the actual temperature. The green line is the pressure compensated temperature. So you see, for example, in this section right here, you see that blue line bouncing all over heck and back? Okay, you see the green line, how that it's fairly smooth? Look down here at the analyzer. Which one better represents what's going on with the composition, PCT or the regular? PCT. It's a simple engineering calculation. So if I control the pressure compensated temperature, and I use that as an approximation for composition rather than the actual temperature, which one's going to do better? PCT. So here I turn on my control. Did I reduce my standard deviation by 50%? Here's the place where I lost my analyzer. Can you see that? All right. So, do you think I made him the money that I said I was going to make him? Yeah. All right. So that's it. That's the example of before and after doing some engineering calculations and doing some very simple controls, improving the controls. Okay. Does that make any sense to you? That's pretty good money, isn't it? That's not bad. Okay. Would that pay your salary for a year? Okay. Probably would. It would for multiple years if it were working for me. Be like a decade. Sorry, no, that's not true. I have to try to beat the stereotype, right? So here's another one we did. I did one down in Sweeney Refinery down in Texas. We did a propylene splitter. You guys know what propylene is? Yeah. What's propylene used for? Polypropylene, plastics. Okay, valuable stuff. This is a $1995. Oh, that's the same one. Next slide. Come on. Come on. Propylene production before was 150 barrels at 2,500 parts per million, increasing propylene production by 10-15 barrels per hour at 3,500 parts per million. 10 barrels times 213 pounds per barrel, 14.5 cents per pound, 24 hours a day, $7,412 a day, 330 run days a year, $2.45 million. Anything to sneeze at? When we started doing work at the Big West Refinery, they were barely profitable. Okay? But because of the process control and because they kept adding processes that made them money, they're now an extremely profitable refinery on the orders of multiple hundreds of millions of dollars a year profit. Okay? Okay, so if you can walk in and you can say, hey, look, I can do some things for you, you're going to be a hero. Okay?
Do these companies usually come to you first, or do you go to them and say, hey, I can make you some money?
You know, I'm not a very good, I've been in business for some time now, but I'm not a very good businessman. That tell you something? Okay. I'm an engineer, I'm not a good businessman. I'm actually not a bad businessman, but I don't do some of the things that are good. I don't go out and knock on doors. It's just not in my nature. I'm a pretty outgoing guy, but I find it hard to knock on someone's door and say, hey, look what I've got to show you. So the way I do it is they call me up with a problem, I go in and help them solve the problem, and then I educate them. So a big part of what we do in process control and what you'll do as engineers, I'll guarantee you, is education. There's a salesman component in every engineer's job, every single one. I don't care where you work or what you do. You're going to have ideas, you're going to have things you think you want to get done. You're going to have to sell someone on those ideas, okay? You're going to have to help them to understand that it's worth their while. Economics is almost always the best way of doing that. There's other safety and other things like that that can do it, but economics is the best way to do that. So thinking about things in terms of economics and how to do the economic analysis to justify. So on this one I made some assumptions, didn't I? I assumed I'd be able to reduce their standard deviation by 50%. I learned that from experience. Is that hard to do? No, not for me. It's trivial. If I'd have gone in there and said, I'll reduce your standard deviation by 90%, what do you think they would have said? Ah, black, oh yeah, right, black magic, yeah, what are you going to do? Yeah, right, we're better than that, right? But if you look at it, I probably reduced it by 80, 90%, okay? So you have to be realistic. My goal is to always give good estimates of what I do, conservative estimates. So when I told these guys I was going to make them $500,000 a year and I made them $1.2 million a year, what do you think they did? They came back and said, wow, that's on our gas plant. That's not supposed to make any money. What would you do if you did the rest of the plant? And so we've done all the process control for the last 15 years. All right? So my way of doing business is to not go in there and try to make somebody pay through the nose. I did come to this company after the first job, and I said, I'll tell you what I'll do. I'll do the rest of your plant, and it won't cost you a nickel. Now, how's that sound? Sounds like better businessman? Yeah. Sounds like the guy selling me a water softener or something to me. But anyway, what I do is I'll take 10% of your incremental benefits. Just 10%. Just like this one, we'll pull a bunch of data before, we'll pull a bunch of data after, we'll run it for a year, we'll see what we make. The incremental benefit, I'll only take 10% of that. 90% of that will be yours. Just 10%. 10% per year for the next 5 years. Okay? So if I did 10% per year for that one, for the next 5 years, I would have made $120,000 a year for 5 years. I would have done all right, wouldn't I? You know what the refinery manager told me? Don't worry about it. Just tell us what your rate is. We'll pay whatever it is. And we did the rest of the plant that way. He didn't want to pay me a percentage because the dollars are big. So I'm getting into other things like a cat cracker and the reformer, alkylation units, things like that. That's lots of millions of dollars a year in Jamaica. Okay? So the answer is I don't knock on doors. They usually come to me. One of the things I'll tell you about business is my business is not what I anticipated it would be. When I started my business, I came back from Set Point. I was Super Mr. Advanced Control. I was a software development manager for this worldwide company. I was all over the world doing this stuff. I had lots of contacts in industry, and I came back and I thought, wow, I'm going to do work in the heavy industries. Work in refineries, chemical plants. I'm going to make my millions and go home and be happy. Well, the first thing I'm out there working on the Big West refinery, and the next thing I know, Central Utah Water. Do you know who they are? Central Utah Water controls most of the lakes and stuff. They control the water flow for most of northern Utah, Provo River, all the other rivers, Jordanelle, Strawberry, Starvation, blah, blah, blah. They have 3 water treatment plants. They come to me and they say, we've got a problem. We've got this company we hired out of New York, and they put in a system called Sidecar, and it's not working. And we had a big problem the other day. Problem up at the Jordanelle Dam. You guys know what Jordanelle Dam is, right? So you know what the problem was? What's the worst thing that could happen to the Jordanelle Dam? It could break. What's the second worst thing that could happen to the Jordanelle Dam? The floodgates would open. The gates would open, right? What would happen if the gates open? Heber would be underwater, right? Okay, because Heber's right below. Okay? That would be bad, wouldn't it? I would contend that that's not quite as bad as what happened to him. The gates closed all the way. What happens if the gates close all the way? Huh? The Provo River dries up. Oops, I'm not good, but that's bad. You know, the only thing worse than killing people is killing fish. Come on, where are the fishermen? Come on. He knows what I'm talking about. All right, I mean, you follow Homer too, you can pump the water out. You kill fish, that's a decade or more before you recover from that. That's a long time, that's bad. So the gates land on the Jordanelle Reservoir, okay? So we went up there and we put in a bunch of stuff that we do all the time in the chemical industry, the refining industry, a bunch of safeguards, right? Can I have a valve slam open or shut in a refinery? If I do, there's a good chance somebody will die. That's not good. Happens all the time, that's not good, right? Okay? So we already build in safeguards, lots of safeguards. We're very good at it. Very, very good at it. So they come to us and say, we want you to retool our system. How much is it going to cost? I said, okay, man, I think about $200,000. I just go, hip hop. Pop that out. That's a salesman. I don't have $1. I reacted to the calculation. I'm not quite that. Anyway, so we did it. But they had a guy working there, and he just started the day that we started working there, and he did most of the panel work, changing power supplies, replacing control. He did most. So we went back and we said, look, you got like $100,000. The project's done. You got $100,000 left. He said, whoa, wait a minute. What do you mean we got $100,000? Well, we're done. Your guy did a lot of the work. He said, what do you told us it would be this much. You haven't charged us that much. Send us a bill. No one comes to us and say, no, we don't want your money. We said, well, you guys good. We helped us. What do you want us to do? He said, well, they said, well, we've got a wish list of things that we wish our system did. I said, well, give us the wish list. We'll work on the wish list until we run out of money. They said, great. We got almost all the way through the wish list, and that was 12 years ago. Who's doing all the control work? We are. Okay? So being honest, one of the things about being who we are is being honest about your work is good. So you don't need to try to cheat people. Just because you can doesn't mean you should, right? So I treat my employees, my clients, everybody the same way. I'm very, very open and very direct with them, which is a good thing on everybody's side. If an employee's not doing well, I'll tell him he's not doing well. I'll tell him why he's not doing well. We'll do what we can to help him get better. Right? Same way with the client. I don't go to my clients and say, don't pay attention to what we're doing because this is top secret proprietary. I'd have to shoot you if you saw. And that's not my approach. My approach is, yeah, have someone stare over our shoulder. Anything you guys can learn is great. It's your system. You want to know as much as you can about it. Okay? The key to good process control is getting the process and the control to work together. Understanding the process is what engineers do. Right? If it's a matter of saying, hey, it goes up, I'm going to open the valve when it goes up, it goes down, I'm going to close the valve, I can train a monkey to do that. I don't need an engineer. I need an engineer because he understands the process. All right? Knowing the process characteristics is the first step in implementing good control and evaluating control performance. Processes with different characteristics require different control techniques. There's no one-size-fits control technique, including multivariable control, which used to be considered the solution to all control problems. Now I'm going to go through just a little simple example. We're almost out of time. I'm going to go, self-regulating process. This is the two most important things you need to know about process control. Two most important process characteristics. I'm going to give them to you right now. Okay? If you pay attention to this next 5 minutes, you're going to be a superstar. Okay? Whenever I go into a refinery or a chemical plant, almost anywhere, most of the problem is they're all doing PID control. It's a standard, 90-95% of control out there is PID control. And they're trying to use PID control on everything, okay? And that's fine. For the most part, it works pretty well. But you have to understand what you're controlling. Is the process self-regulated? What I mean by self-regulating control is if I open a water valve a little bit, what happens to the flow rate? It increases and stabilizes out at a new value. If I open it a little more, it increases and stabilizes out at a new value. Just like that. That's a self-regulating. If I increase the heat to the bottom of a distillation column, the temperature goes up, stabilizes out at a new temperature. Does that make sense? It's called a self-regulating process. Okay? In a self-regulating process, you use P, proportional, integral, and maybe derivative if it's got a long lag time, but certainly PI control. Okay? You have to have the integral, otherwise you've got steady state offset. Okay? In an integrating process, I make a change. Let's say that this is my thing, and I make level loops open. I make a change in my outlet flow. Let's say I increase my outlet flow. What's going to happen to my level? It's going to go down. How long is it going to go down? Forever, until it runs empty. Or if I reduce the outlet flow, how much is it going to go up? Until it what? Do you see the difference in the reaction? So for an open loop step, one of them is self-regulating, the other one's integrating. In this particular one, if you have an integrating process, you use no integral control. None. All right, now you guys can go out and save the world. That little technique probably got half of the benefits on that distillation column that I told you about. Just knowing that little bit. Okay, so you can study Laplace, you can study Bode, you can study all kinds of tuning techniques that you want to, but just knowing that will get you most of the way there. Okay? So how do you like that? That were 50 minutes? There you go, that's your lecture. Not a big deal, okay? Integrating processes use proportional control. Sometimes you can use a very small amount of integral action. Okay? When I say a small amount of I don't mean the I value's got to be small, because if the TI sometimes is in the denominator. If you use a small I and it's in the denominator, how much integral action do you get? A lot. So you got to know if the I is in the numerator or the denominator. Right? I mean, we're really good engineers. You know, if it's the numerator or the denominator. It's another gotcha. Okay? If it's reset time, if they call it time, it's in the denominator. If they call it reset rate, it's in the numerator. Okay? Self-regulating process, P&I give me all we need depending on the relative speed, get them. That's it. Okay? So that's it for that. Now what I want to do is just spend the rest of the time. I can talk about that. I can talk about that. I can talk about that, but I'm not going to. Okay? I want to spend the rest of the time answering any questions you guys have got about control, what's important, what's not important, or just engineering in general, chemical engineering. We do work in just about any industry you can think of. Pharmaceuticals, manufacturing. So Hexcel, they make carbon fiber. We do a ton of control work out there. 3 of the 5 refineries on the Wasatch Front. The water industry, the pharmaceutical industry. We make gun safes. We make, you name it. We do wastewater treatment plants. We do water treatment plants. We make cheese. We make dog food. We make, you guys name it. Give me anything. Come on. Tell me something you think process control or chemical engineers don't have anything to do with. Anything. Come on. That's a challenge. All right, you guys?
Diapers.
Power bait.
What? Power bait. What's in power bait? He's got a look. Chemicals. Okay, there's a lot of chemicals. There's artificial coloring, things like that. All those come from the chemical industry, right? Go ahead. What's next? Okay. What was that?
Hollywood.
Hollywood. Have you seen the faces on those girls? That's all chemical industry. What else? Anything else? You know, I did this thing at the University of Utah, and someone said, prostitution! You know, and I said, come on. You guys, you really want me to go into all the ways that the chemicals help those prostitutes? The bearded guy in the back. Computer programmers? We use computer programmers. You know, the reality is that computer programmers are not successful at all in this industry. There are some computer programmers that try to get into this industry, but they have the problem is they can do a lot of theoretical programming. They have a really, really, really difficult time knowing how to apply it to real stuff. So one of the problems that so for me, for example, in my PhD, I did what I call practical process control. Practical process control is there's a ton of theory in process control out there, and there's a tremendous amount of good theory in process control. But what are they doing in industry? PID control, maybe some other simple stuff. So the question is why? If there's all this great stuff, why are they using PID on very complex processes? Why does their control stink so bad? Well, there's a huge gap. The people in industry say those people in academia, they're academic. If something's academic, what does that mean? Yeah, it's not real. It doesn't have any value, right? That's academic, right? Okay. So that's their perception of academia. And the academics say, wow, I remember when I got my PhD at the University of Utah, there was one guy on my committee that says, so what? And that's been done in theory 100 times. So what's the big deal of doing it in practice? You know, that's not worthy. Okay, you see the problem with that? So there's this huge gap between theory and practice. People like myself, Dr. Hedegren, and others are trying to close that gap. Okay, and that's a huge value, because not all processes can be controlled with PID control. Particularly when you get into interactive processes, nonlinear processes, processes that are just all kinds of different things that are extremely important for safety, for dollars, for quality, for all kinds of things, all right? So, does that make sense to you? Okay. So, programming a nonlinear algorithm is something a computer science guy can do great. Knowing how to use that nonlinear algorithm and put it into an application piece of software is really something you need a good engineer to do.
If someone really wants to go into process control, they're interested in it, would you recommend them to go start off with process engineering first to get that strong background and then go to process control? Or just take a job offer trying to do process control?
Either of the paths are okay, but if you're going to do process control, take a process control job in an industry that is doing process control on processes. Okay? At APCO, we usually hire guys that have done both process and process control. So they'll start out as a process engineer or a process control engineer in a process plant, okay? And I don't care if it's a water treatment plant, I don't care if it's a refinery, a chemical plant, a dog food plant, I don't care what plant it is. It's just so that they can get used to the relationship between how to get from the computer all the way down into the process and understand how it all works together. Does that make sense to you?
Do you use PLCs or?
Yep, we use PLCs a lot. So there's two different kinds of computers primarily used for process control. You guys are using, what are you guys using in the lab now?
LabVIEW.
LabVIEW is not one of them, okay? LabVIEW is not one of them. So LabVIEW is a PC-based control system that's never used in industry, okay? Never used in industry. They'll use what's called PLC, which stands for Programmable Logic Controllers. There's 100 different kinds out there. One of them is called Rockwell. One of the things I'm thinking about doing is Rockwell has approached me about making a gift to the chemical engineering department here to put them in their lab. And I have to talk to someone about that to see if they want to do it. Problem is you have to have somebody to implement it, or, you know. But that's a real industrial system. That's what's going into the Big West refinery right now. It's being swapped out. The other kind of system is called a DCS, Distributed Control System. And that's historically a much bigger system, like the Bailey system was. Now the Bailey system's 25 years old, so you wouldn't expect a computer 25 years old to be great, right? So anyone who worked on the Bailey says, oh, it stinks so bad. I said, yeah, well, fire up your computer from 25 years ago. Tell me how good it is, you know? So these control systems are very much tied to the computer industry. And so after a decade or so, 10 to 15 years, you need to replace them. And that's just the way they work with PLCs. And so you learn programming languages associated with PLCs. There's IEEE 11.5.61 dash blah 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 blah. You know, there's a language that has six languages that you can program in there, and we do a tremendous amount of work in those. Okay, oil gas industry, that's also areas we work in. Anything else? Any other questions? Don't you guys want to ask how much you make? Okay. A process control engineer. If you're a good process control engineer, I could get you a job anywhere on the Wasatch Front for making top dollars. So I've got a friend of mine that's been out of school for about 10 years. He's making about $125,000 a year. Okay? The reason, there's always positions open in process control. Okay? Always, 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 always. And it's because it's a little more difficult than your steady state calculations, you're doing heat transfer, mass transfer, things like that. You have to deal with that. Any other questions? Thank you guys very much.